Yeah, just a minute.
Yes,
Yeah.
I am. Yeah, I am trying to sharing my screen. Is it visible?
Yeah, yeah, sure.
Is it visible my screen?
Yes, it is visible. Priyanshu, go ahead.
Yeah. Okay. So at first, I want to thank KSM and the organizing committee for giving me opportunity to present this paper. Thanks to all. So the table of contents is introduction and preliminaries about Lie algebras, result related to Virasoro algebras, the main result and references. So initially, throughout all the throughout this presentation, all vector spaces are taken for C. By Lie algebra L, we mean is it's a vector space endowed with a bilinear map from L cross L to L, which has two properties: bracket xy equal to minus bracket yx. This property is called as antisymmetric property, and bracket x comma bracket yz equal to bracket xyz plus y bracket xz. This property is known as Jacobi identity. Some examples of real algebras are GLN, the set of all n by n matrices; SLN, the set of all n by n matrices with trace zero entries; associative algebras. GLV is a particular class of associative algebras for some vector space V. Actually, these are all the algebras with the bracket operation bracket AB equal to AB minus BA. Moreover, one more example of infinite dimensional Lie algebra is derivation algebra on N, Laurent polynomial ring over n variables. Moreover, given any Lie algebra, one can construct a new Lie algebra from the old one. The example 1.3 shows this kind of construction. Suppose one have a Lie algebra L and a commutative associative algebra B. Then one can construct a Lie algebra L tensor B with the bracket operation bracket x tensor A, comma y tensor A dash equal to bracket xy tensor A dash. This kind of Lie algebra is generally called as loop algebra. Representation of real algebras. By a homomorphism between two real algebras, L1 and L2, this is a linear map phi from L1 to L2 which satisfies the Lie bracket, which preserves the Lie bracket. A representation of a Lie algebra L is a Lie algebra homomorphism phi from L to GLV for some vector space V. The dimension of the vector space is called the dimension of the representation. A representation is said to be irreducible if there is no non-zero proper sub-representation. Vector space V is said to be L module if the following properties holds. Ax plus by action on V is Ax dot V plus by dot V. X dot au plus bv is equal to Ax dot u plus by dot V. Bracket xy dot V equal to x dot y dot V minus y dot x dot V. For all xy in L, ab in from the field and uv from the vector space V. It is easy to see that above two notions are equivalent. These two notions are equivalent in the sense that given any representation, one can construct a L module. On the other hand, given any L module V, one can construct a representation. Consider the infinite dimensional Lie algebra with basis bi, c, I in Z, and defining relations bracket di dz equal to j minus I di plus j plus del ij iq minus I by 12c bracket di, c equal to 0. Here c is the center element of this Lie algebra. This Lie algebra is known as Virasoro algebra. We denote this Lie algebra as V. Let V plus equal to span of vi I greater than 0, V minus equal to span of di I less than 0, and V0 equal to span of V0, c. Then this Virasoro algebra has a triangular decomposition like V equal to V minus direction V0 direction V. Now we are going to define weight module for Virasoro algebra. A module V for V is said to be weight module if the action of D0 on V is diagonalizable. That is, that V can be decomposed as V equal to direction of V lambda, where V lambda equal to all those V in V such that V0 dot V is equal to lambda V. The spaces V lambda is called weight space of V with respect to the weight lambda. Now we define highest weight module for Virasoro algebra. A module V for V is said to be highest weight module or lowest weight module if there exists a non-zero weight vector V in V such that V plus action on V is 0, and it will be called lowest weight module if V minus action on V is 0. With the one more property that uv dot v equal to v. Here uv is the Universal alpha-level algebra of the Virasoro algebra. A module V for P is said to be a module of intermediate series if dimension of non-zero weight spaces be all 1. Now, in 1992, Matthew gives a classification theorem for Virasoro algebra with finite dimensional weight spaces. This result states that an irreducible module for V with finite dimensional weight spaces is either a highest weight module or a lowest weight module or a module of intermediate series. Later, in 2007, Raimund Zhao and Majicho proved that instead of taking all finite dimensional weight spaces, if one take an weight space of infinite dimensional, then they proved that suppose V is an irreducible module for V with an infinite dimensional weight space, then all its non-zero weight space should be infinite dimensional. From there on, large class of module for Virasoro algebra with infinite dimensional weight space has been studied actually. In particular, for loop Virasoro algebras, this kind of classification also done. Consider the algebra V tensor B for some commutative associative finitely generated unitary algebra B. And note that the triangular decomposition of V induces a triangular decomposition of V tensor B, like V tensor B equal to V minus tensor B direction V0 tensor B direction V plus tensor B. We define weight module for V tensor B similarly like V, because D0 is also lies D0 tensor 1 particularly also lies in this V. So you can define weight module similarly like as V. Moreover, we call a module V for V tensor B as highest weight module or lowest weight module if there exists a non-zero weight vector V such that V plus tensor B dot B equal to 0 or V minus tensor B dot B equal to 0 and V is cyclic in the sense U V tensor B action on V will be whole of V. In 2012, Savage classifies irreducible module for V tensor B with finite dimensional spaces. He proved that suppose V is an irreducible module for V tensor B with finite dimensional weight spaces, then V is either a highest weight module or a lowest weight module or a module of intermediate series. But so actually the classification theorem for V tensor B and V with finite dimensional weight spaces in some sense have same kind of behavior. Either they will be highest weight module or a lowest weight module or will be a module of intermediate series. But the thing that suppose V is an irreducible module for V tensor B with an infinite dimensional space. In this case, we don't know what happened about all other weight spaces. What we have answered for Virasoro algebra case. In that case, actually, they are all the weight spaces should be infinite dimensional. But in this case, this answer is still open. On the other hand, a large class of irreducible module for V with infinite dimensional weight space found. In particular, in 5, a Chang studies irreducible problem for tensor product of highest weight module VCH, VCH, and irreducible intermediate series modules V alpha beta for V, where CH alpha beta are complex number. Moreover, all the weight spaces of these modules are infinite dimensional. Later, isomorphism class of the above mentioned module, this kind of module, the tensor product of these modules have been found at 7. Here we define Varma module for Virasoro algebra. Let C comma H be C, B in C such that CH not equal to 0, 0. Let CCH is span of eta 0 be a one-dimensional module for V0 such that D0 action on eta 0 is H eta 0 and C action on eta 0 equal to C eta 0. Extend CCH to a module for V0 direction V plus by defining the action of V plus as 0 on CCH. Then define Varma module. Actually, this is the module of this is the induced module. So and define Varma module MCH as U V tensor with CCH. Actually, CCH is a module for V0 direction V plus, and V0 direction V plus is subalgebra of V. So you can take the tensor product over this, and this kind of module are called Varma module. And let TCH be the unique irreducible quotient for MCH. Now we give a classification theorem due to Kaiming Zhao and to other authors. Before that, we give some construction actually. So it is well known that there is a intermediate series module V alpha beta for V with two parameters alpha beta. As a vector space, this V alpha beta is direct sum of C V and n running over Z. And V action on V alpha beta is given by dn action on Vk as alpha plus k plus n beta vk plus n and c action on vk equal to 0 for all k n in z. For convenience, we denote v dash alpha beta equal to v alpha beta if v alpha beta is irreducible. Now, there is a result due to Keck and Reiner 1987 that the V modules V alpha beta is isomorphic to V alpha plus m comma beta for all m in Z. The V module V alpha beta is irreducible if and only if alpha does not belong to Z and beta does not belong to 0. V00 has a unique non-trivial proper submodule CV0 and denote V dash 00 is equal to V00 cosine tau by CV0. In particular, as this submodule CV0 is a unique non-trivial proper submodule, so this V dash 00 is actually irreducible. Moreover, V01 has a unique non-zero proper submodule V dash 01 equal to direct sum of CVI I not equal to 0. And V dash 00 isomorphic to V dash alpha 1 for all alpha and C. So one can see from this result that the modules V dash alpha beta, where alpha is running over 0 less equal to real alpha less than 1 and beta not equal to 1, then all these modules are actually irreducible modules for V, and these are all distinct irreducible modules. Now this result classifies the tensor product of these two modules. Suppose C1, C2, H1, H2, alpha 1, alpha 2, beta 1, beta 2 be in C such that 0 less equal to real part alpha 1 less real part alpha 2 less than 1 and beta 1, beta 2 not equal to 1. Then V C1 H1 tensor V dash alpha 1 beta 1 isomorphic to V C2 H2 tensor V dash alpha 2 beta 2 if and only if C1 equal to C2, H1 equal to H2, alpha 1 equal to alpha 2 and beta 1 equal to beta 2. In particular, actually we generalize this result for V tensor V and produce a class of a large class of irreducible modules for V tensor V. So here I construct a large class of irreducible modules for V tensor V with infinite dimensional weight spaces. So we define a V tensor B module structure on V alpha beta, where V is a commutative associative unitary algebra. Let psi from B to C be an algebra homomorphism such that psi 1 equal to 1. Define a module structure on V alpha beta by dn tensor B action on Vk is equal to psi b times alpha plus k plus n beta times Vk plus n and C tensor B action on Vk is 0. Clearly, these V dash alpha beta are irreducible for V B since they are irreducible for V and V B is bigger algebra than V. We denote these modules at V dash alpha beta psi. This psi is coming due to the thing that to define this action we need one more parameter psi. Let phi from V0 to C be a non-zero one-dimensional representation of V0, and let eta be a basis vector of this one-dimensional representation. Then x tensor B action on C eta will be phi of x tensor B dot C eta, where C in C, x in V0 and B in B. Now we extend this C phi to span of eta to a module for V0 direction V B plus by defining action of V B plus as 0 on C phi, and then construct the Varma module M phi is equal to this. Let n phi be the unique maximal proper submodule of M phi. Then V phi equal to M phi by N phi is irreducible highest weight module corresponding to phi. We consider V phi be the highest weight vector for this V phi. Now consider the module V phi alpha beta psi equal to V phi tensor V dash alpha beta psi for V B. Clearly, this is a weight module for V B, and V phi alpha beta psi have weight space decomposition like this, where V phi alpha beta psi phi d0 plus alpha plus n equal to direct sum of this thing. From this thing, it is clear that V phi alpha beta psi has all infinite dimensional matrices, because this thing is running infinitely many times, and the thing is all V phi d0 minus phi have infinitely many non-zero weight spaces. Now we give a lemma which will be crucial in all the theorems actually. V phi alpha beta psi is generated by V phi tensor Bm m in z, or V phi tensor Bm m in z minus 0 according as alpha beta not equal to 0 0 or alpha beta equal to 0 0. That is, whenever alpha beta not equal to 0 0, then V phi alpha beta psi will be generated by V phi tensor Bm m runs over whole of z, and when alpha beta equal to 0 0, this will be generated by V phi tensor Bm m runs over only m in z minus 0. next result is the set of all endomorphism of V phi alpha beta psi, that is V over the V phi alpha beta psi Virbi module morphisms are actually C times identity. And from this thing, it is clear that in particular V phi alpha beta psi are all indecomposable modules. Now, we know that all irreducible modules are indecomposable, but not the converse. So right now, we find a condition on which V phi alpha beta psi will be irreducible. For alpha plus beta not in Z, V phi alpha beta psi is irreducible if and only if V phi alpha beta psi is cyclic on every V phi tensor Vm. That is, by cyclic we mean that universal and available algebra action of V phi tensor Vm should be whole of V phi alpha beta psi for all M in J. Now using this result, we prove a sufficient condition for irreducibility of these modules. Suppose alpha plus minus beta not in Z and B in B such that psi be non-zero. Then V phi alpha beta psi is irreducible if phi restricted to D0 tensor ideal generated by B is 0, where this denotes the ideal generated by B in B. We assert that D minus 1 tensor B dot D phi equal to 0. If not, then D1 tensor A dot D minus 1 tensor B dot D phi will be actually 0. Moreover, D2 tensor A dot D minus 1 tensor B action will be also 0. And from these two things, one can easily see that all the converts D3 tensor A, D4 tensor A all will be at 0 because lubricate D1, D2 equal to D3. Therefore, we have that D minus 1 tensor B dot B phi is actually a high state vector for B phi, but it can't be because the high state space for B phi have only dimension 1. So, and all the vectors of D minus 1 tensor B dot B phi will shift towards the negative side of the B phi. Now, B minus 1 tensor B dot B phi tensor Bn plus 1 equal to this. After computing this action, we will have this will equal to psi b of alpha plus n plus 1 minus beta B phi tensor Bn. From this, it is easy to see that U Vb of B phi tensor Bn is actually subset of U Vb of B phi tensor Bn plus 1 for all n in J. On the other hand, D1 tensor B of B phi tensor Bn equal to psi b alpha plus n plus beta B phi tensor Bn plus 1. This implies U Vb V phi tensor Vn superset of U Vb V phi tensor Vn plus 1 for all n in J. From these two, we have U Vb V phi tensor Vm equal to U Vb V phi tensor Vn for all Mn in Z. Now, we have that V phi alpha beta psi is actually generated by V phi tensor Vm. So, and these two are all equal. Hence, by theorem 3.3, we have that these are cyclic on every V phi tensor Vm, and therefore these modules are irreducible. Now, we should prove that if V phi alpha beta psi is isomorphic to V phi 2 alpha beta psi 2, this will imply psi 1 equal to psi 2. So, to prove psi 1 equal to psi 2, it is sufficient to prove that kernel psi 1 equal to kernel psi 2, because then it is easy to see that this will imply psi 1 equal to C psi 2 for some C in C. And now, psi 1 1 equal to psi 2 1 equal to 1 gives that psi 1 equal to psi 2, C equal to 1. Let kernel psi 1 not equal to kernel psi 2. Without loss of generality, we can assume there is B in kernel psi 1, but B does not belong to kernel psi 2. Since T is an isomorphism between these two, so there exists V phi tensor Vk has a pre-image under this T. Since T is an isomorphism, so the pre-image of this non-zero vector will be a non-zero vector. Let T of this equal to this, and this xi will coming from V phi phi d0 minus I because of the weight space decomposition of B phi alpha beta psi. Now, assume beta to non-zero. If beta to non-zero, then choose L much greater than n such that alpha 2 plus kx L beta to non-zero. Then from 5 we have T of this equal to this. And now, since L is much greater than n, the action on both of this component will be dl have the action on both of this component of dl will be 0. But on the other hand, in this side, the action of dl tensor B on Vk will gives us alpha 2 plus k plus L beta 2 times something. So left hand side action will be 0, but right hand side action will be non-zero. So this can be possible. Moreover, if we take beta 2 as 0, then we just consider L much greater than n. Then we have the right hand side of 6 becomes psi 2 b alpha 2 plus k this, and this will be non-zero since if alpha 2 plus k equal to 0, then this will imply that alpha 2 in z, but alpha 2 in z implies alpha 2 equal to k equal to 0, because we have 0 less equal to real part alpha less than 1. From this we will have this thing. Now it will give the final classification theorem between these two modules, that b phi 1 alpha 1 beta 1 psi 1 isomorphic to b phi 2 alpha 2 beta 2 psi 2. You can only psi 1 equal to psi 2, phi 1 equal to phi 2, alpha 1 equal to alpha 2, and beta 1 equal to beta 2. Now actually this result generalizes the result of priming Zhao in Dirichlet tensor case, because in their case instead of phi 1 there was only two variables c and h, wherever in our case it is actually a linear function and there was no psi, and in our case this is a any algebra morphism from B to C. So let T from this to this be an isomorphism and assume that alpha 1 beta 1 non-zero. Since T is an isomorphism for L in Z, the image of B phi 1 tensor BL will be a weight vector of same weight as that of this one. So let T of this equal to this. Now use the action that T of for all m in greater than k. Use the action T of dm dn action on B phi 1 tensor BL is equal to dm dn action of T V phi 1 tensor BL, which gives us actually alpha 1 equal to alpha 2, beta 1 equal to beta 2, and T of B phi 1 tensor BL is equal to CL dash B phi 2 tensor BL for some CL dash in C star for all n in Z. Here this L will running over Z because of the fact whenever alpha beta not equal to 0 0, we have that V phi alpha beta psi is generated by V phi tensor Vm M running over Z. Now consider the relation T of B0 tensor B dot V phi 1 tensor BL equal to D0 tensor B T V phi 1 tensor BL and T C tensor B dot V phi 1 tensor BL equal to C tensor B T V phi 1 tensor BL. Then using lemma 3.5, that is psi 1 equal to psi 2, 8 and 9, these two relation, and just using the action, we can easily see that phi 1 d0 tensor b equal to phi 2 d0 tensor b, phi 1 c tensor b equal to phi 2 c tensor b for all b and b. That is phi 1 equal to phi 2. Yes. Similarly, in the case of alpha 1 beta 1 equal to 0 0, one can see that t phi 1 tensor bl becomes cl dash t phi 2 tensor bl cl dash in C star, but in this case l run over z minus 0, and from there we can conclude that phi 1 equal to phi 2, alpha 1 equal to alpha 2, beta 1 equal to beta 2. Again by lemma 3.1, and this we have that the only possibility is alpha 1 equal to alpha 2, beta 1 equal to beta 2, psi 1 equal to psi 2, and phi 1 equal to phi 2. These are the references. Thank you for your time.
Questions?
This complex.
Any questions online? You can check the chat.
It's the chat, but like 7, we can see the message. So that's the old one. Some echo.
No, that's an old chat. There are no questions.
I think no more
Let's
questions.
thank the speaker again.